Welcome back. Last time we introduced the concept of kinetics of the reactions or the rate of the reactions. And the most important thing we learned was that we can measure how fast a reaction is happening or the rate by determining how the concentration of the reactants is decreasing or how the concentration of the products is increasing in reference to the time. So how much the molarity changes by a given time. And we saw after we did some manipulation that the rate is better expressed by doing this type of formula where you have the rate constant, the concentration of the reactant elevated to a given power. And we saw that those powers can be obtained by observing what happens during the experiment when you change the initial quantity and measure how fast the reaction happens. So that's where we left it last time. So we're going to go deeper now with this concept. What we're going to do now is we're going to see once more in a different way how the concentration changes given a specific time in terms of the rate. We're going to learn a whole new concept which deals with the integrated form of the rate law. So we're going to see how mathematicians took the rate law, R equals K concentration to a power, did integration to it, and transformed that law into a formula of a straight line. Mx plus b. And the power of being able to do with this formula now is that you can plot y versus x, and that will give you the value of the slope m, and depending how your formula looks, that can be very powerful because you usually try to make y and x to be easily measurable quantities. So that's what the integrated law is going to do. It's going to take our rate constant law, R equals the rate constant times the concentration of the reactant to a specific power, and it's going to make it look like a straight line equation. So we're going to call that the integrated rate law because we use mathematical integration to do that. And once we have that formula, you can start predicting what will be the concentration after a given time. So it gives us the power of prediction or being able to control a chemical reaction. And then we're going to start talking about half-life and how that relates to the rate constant, specifically for the first order reaction. That's the one that we're going to use the most. And let's get this out of the way. What is half-life? If I have, let's say, 50 grams of something, and an amount of time goes by, and at the end I have 25 grams, that amount of time required for this to go to half of what it was is what we call the half-life. So half-life is nothing more than the amount of time required for something to be cut into half, or for a reactant to be consumed by half. And we're going to be using that a lot when we do nuclear reactions toward the end of the semester. So let's go ahead and do these objectives so we can get familiar with that. So the first thing I want to show you is the integrated laws. So these are going to be my integrated laws. And remember that we discussed that if you have the rate formula, rate equals k a to the power of 1, we call that first order. If this happens to be 2, we call that second order. If it happens to have two reactants, and one of them is 1 and the other one is 1, then we say that that it have an overall order of 2, because 1 plus 1 equals 2. So that's what we are referring to when we're talking about the order. So after we take a rate law, like the one that I just showed you for first order, and we give it to our friends, the mathematicians, and they manipulate it with integration to make it look like the equation for a straight line. This is what it's going to look like. On this case, this would be the y. The rate constant would be the slope. Time would be the x-axis. And ln AB is what we call the intercept. So let's take a closer look at these terms in here. So this is what we call the concentration at a given time. So for example, if I want to see what the concentration would be at 50 seconds, that would be the concentration at 50 seconds. This here means that this is the initial concentration. So whenever you begin a reaction, you know exactly how much you're beginning with. That's what this symbol means, is the initial concentration. You already know this is the rate constant, and this is going to be the time that we're looking for. So if we want to see, if we start with, let's say, 3 molar, and we want to see how much remains after 3 seconds, then this will be when the time is 3 seconds, and this is what we're trying to find out, how much remains after 3 seconds. So like I was saying, this is then the way a first order reaction will look in the form of a straight line equation. This is the way a second order reaction will look. And this is the way a zero order reaction will look. And why is that important? Well, that is important to know because these are integrated laws. So if we do a graph of this versus this, so like ln a t versus time, this is going to be the slope and it's going to be negative. So we know it's going to look like something like that. And it has to be a straight line. If I plot this versus that. For the second order, this will be my y, so 1 over the concentration. And this will be my x, my time, and the rate constant is positive, so it will be something like that. And on the zero order integrated law, we're going to plot, this will be my y, this will be my x, and we will have a negative slope. So once more, something like that. So keep that in mind, that this is the most important concept about the integrated laws. When you plot the y versus the x, it has to give you a straight line. Remember, if you remember that, you're going to have a lot of power. So we have an experiment. So we have data from an experiment in which we were tracking the time versus the concentration. So we have the reaction set up with some machinery that allow us to know the concentration. So before the reaction began at 0 seconds, we started with 1 molar. After 25 seconds, we measure it again, and it's now 0.822 molar. At 100, it's going to be 0.58. At 125, it's going to be 0.337. First thing that I want you to notice is the concentration is decreasing. Does that make sense? Yes, definitely it makes sense, because we have a reactant, there's a reaction happening, so the reactant is being consumed. If the reaction goes to completion, this should go all the way to 0. But we're going to learn very soon in the next chapter that reactions rarely go to completion because they reach equilibrium at some point. So that's the data that we're interested on. And the question is this reaction that I'm running here, in terms of kinetic, would it be first order, 0 order, or second order? And what we're going to have to do is the following. If we want to check for first order, we will plot ln AT, that will be my y, versus my x, which is going to be time. If we want to check for second order, we will plot 1 over the concentration versus the time. And if we want to check for 0 order, we will plot the concentration at a given time versus the time. Whichever one of those three give us a straight line, that's the order that we're dealing with. So that's what I told you. The most important thing you need to remember is that when you plot y versus x for any of these integrated laws, you have to get a straight line. So we're going to take that data and we're going to manipulate it to plot it for each one of them. So let's begin with let's do this here. Let's begin with 0 order. So like I told you before, for 0 order, you're going to plot the concentration versus the time. So when we take this data, and that's going to be our x, and the concentration without doing anything to it, it's our y, and we plot that versus the time, this is the line we get. When you look at that line, does that look to you like a straight line? And the answer is no. This is not a straight line. Therefore, immediately, this tells you this reaction is not first order, because I plot concentration versus time, like we saw here, and I didn't get a straight line. So it's not first order. So let's check it again. So let's check for first, it's not 0 order, sorry. So let's check for first order. So which one will be first order? This will be my y, and this will be my x. Remember, y equals mx plus b, a straight line. So this is my y, and my x is my t. So if I plot the natural logarithm of the concentration versus the time, I should get a straight line. So let's find out. So we took the concentration and we found the natural logarithm. So these are my y values, and my time is just like this. I plot this against the time, and I came up with a straight line. Not only a straight line, the slope is negative, right? So this is definitely a first order reaction. My slope is negative. When I plot this against this, I get a straight line. So my reaction is a first order reaction. So that's how we use the integrated laws to determine what type of order my reaction is. That means that if I were to write the rate law the basic way, not the integrated, but the basic way, it would be R equals K and 205, right? From here to the first, because I just determined that this is first order. But if it's to the first, we don't put it there. So that would be a rate, that would be the rate law first order for this one. And we know it's first order because we use the power of the integrated law to do a graph and determine the order. Because we got a straight line when we plotted natural logarithm of the concentration versus the time. So we did this part of the problem, determine the order. First order. We know it's first order. So now that we know that, now that we had that power, can you predict the concentration of dinitrogen pentaoxide after 250 seconds? And the answer would be, yes, we can do that. So how are we going to do that? Well, we know this is first order, so the integrated law is going to be the concentration of N2O5 at 250 seconds equals minus KT plus the natural logarithm of the initial concentration of dinitrogen pentoxide. So that would be the initial concentration. So where do we find the initial concentration? At time 0. So the initial concentration at time 0 is 1. So the initial concentration at time 0 is 1 molar. So we have one of the values. So this is the natural logarithm of 1.00. What about the time? Well, the time we know is 250 seconds. 250 seconds will be my time. What about the K? Well, the K, remember, the K is nothing more than the slope of the line. So Excel can do that for me. So that's my slope, which is the same as my K value. So my K value in this case is going to be minus, it's a minus there, right? Minus 0.0078. And this will be the natural logarithm of N2O5. You can put this on your calculator. You can put this on your calculator, and then you're going to get the result for this. So the number that you're going to get is going to be equal to the natural logarithm of N2O5, right? But that's not what I'm looking for. I'm looking just for that. So we're going to get rid of the logarithm by doing the inverse of the logarithm, and we do it on both sides. So whatever number you found, you put it on your calculator. This cancels that. So once you put this on your calculator, that's going to be your answer. So once more, the most important thing to remember is that your rate constant value is going to be the slope of your straight line. In addition to that, you have the table with all the experimental data, right? This table here. And this table here gives you the initial time, which gives you the initial concentration, which is what the formula gives you. Remember, the formula is ln of the concentration at a given time equals minus kT plus ln of the initial concentration. So you get this from the experimental data, you get this from the graphical slope, and then it's just a math problem. But for us to be able to do that, we needed to determine the order of the reaction first, so we knew, so that we knew exactly the formula that we needed to use. And we did that by graphing y versus x, and whichever gave us the straight line, that was the order that we know. So this is first order, this is second order, and this is zero order. So that's how you use the integrated law. So let's do another problem. The following reaction is monitored as a function of time. We do a plot, so we're gonna graph 1 over AB, or the reciprocal of AB, versus time. So let's go back and check that out. The reciprocal versus time. Here are our formulas. So this is my y, this is my x, this is my y, this is my x, this is my y, this is my x. Which one has reciprocal? That one has reciprocal. So we are trying to see if this is second order or not. So we plotting to try to find out if it's second order or not, and when we do, we get a straight line. So that means we're dealing with second order, so the rate law is R equal the rate constant times the concentration of AB, right? It's always the reactance to the second order. So that would be our rate law. And we know that the integrated rate law is 1 over AB at a given time equals KT, the K is positive, plus 1 over AB initial. So we have our rate law, we have our integrated rate law, because we know from the graph that we did that this is second order. And the question is, what is the value of the rate constant? Well, it tells us also that when we did the graph and we got the straight line, we came up with a slope of that value. The slope is nothing more than the k. So if we go back to the formula, this is the formula of a straight line, right? And I know I'm repeating myself, but it's very important. Where my y is this, my x is this, and my slope is my k. So if I know the slope, which I do on this case, then I know my k. So this is the value of my k constant, or my rate constant. So that question has been answered. Write the rate law for the reaction. We know that the rate law equals R. Now we know the value of the K, right? 0.055 over molarity. And that's going to be multiplied times the concentration of AB to the second order. So all that we got it because we were able to graph. So that will be my rate law. What is the half-life when the initial concentration is 0.55? You know the definition of half-life. The definition of half-life is the time required for something to be cut into half. So what is the half-life when the initial concentration is 0.55? So this is telling us, so we're trying to find the time at, which the concentration can get cut in half. We call that half-life. We know that the initial concentration is 0.55. So we know that the initial concentration is 0.55. We know that the K is 0.055 over m, or n to the minus 1. And we know that AB at a given time, which is going to be at the half-life time, we know that it's going to be half of this. So 0.55 divided by 2. So now, using the math that you know, are we down to only one variable? And the answer is yes. So mathematically, you can solve that. And whatever time you find, that's going to be your half-life. So how did we do this problem? We did it knowing the definition of half-life. Is the time required for the initial concentration to be cut in half. So we took the initial concentration and we cut it in half. And we fill up everything else that we already knew. And then we have the last question. And the last question will be, if the initial concentration is 0.250, so the initial concentration is 0.250 molar. We always do molarity, right? And the reaction mixture initially contains no product, so product equals 0. So a typical reaction, by the time you begin, you have no products. You haven't done anything. So if the initial concentration is 0.250, what it's asking is, can you find the concentration of A and the concentration of B after 75 seconds? So you started the reaction with AB. How much of this and this you made after 75 seconds? That's what it's asking. So how can we do that? Well, this is how we do it. If we know how much reactant we begin with, and we know how much reactant we end up after 75 seconds, the difference is how much it was consumed, right? And if I know how much reactant was consumed, then I can use a stoichiometry to find out how much product I made. For this particular problem, the stoichiometry is easy. For every one of these, you get one of those. So if I find out, so let's say we're starting with 250, right? If I'm starting with 0.250, that's the original concentration. And at the end, I find out that I have 0.150. We're talking molarity, right? That would be my concentration after 75 seconds. So to go from there to there, some of the reactant was consumed, and the exchange will be 0.100, right? 0.250 minus 0.150 is 0.100. So that means, if that was the case, and just giving an example, that means that I have 0.100 molar of AB, but I am not looking for AB. I'm looking for the molarity of A, right? And from the balance equation, I know that for every molarity of A, I'm going to need one molarity of AB. That cancel with that, and that will give me my result. Basic stoichiometry from 1411. The question is, the 14, the general chemistry 2 or 1412 question is, how do we find how much remained so we know that the difference is how much it was consumed? So let's go back to 1412. Since we know this is a second order reaction, right? We know that 1 over the concentration of AB at 75 seconds is going to be equal to KT plus 1 over the initial concentration. Do we know the initial concentration? Yes, we do. Initial concentration is this much. So let's go ahead and put that in there. So that's going to be 0.250, right? And you don't necessarily have to put the M. The brackets tell me that that's molarity. Do I know the K? Yes, I know the K. The K is 0.055 over molarity, or n to the minus 1. Do I know the T? Yes. It's telling me that the T is 75 seconds, right? So multiply by 75 seconds, right? So I'm multiplying this times this. And do I know my I know my K, I know my T, I know my initial concentration. So with that in there, I should be able to find that. So once I find that, the initial minus what I find there tells me how much was consumed. And then I do my stoichiometry. So that's how you will approach a problem like that. So here's your daily work. So based on what you just learned, go back and forward as much as you need. See if you can answer this problem. You are to determine the order. So how do we find the order of a reaction given time and concentration? You have to determine the value of the rate constant. Hint, you can use Excel, right? And once you do that, can you predict how much of the reactant is going to remain after 25 seconds? So let's do another problem here. So the decomposition of SO2Cl2 have a rate constant of this. So it's giving us the K value. What is the half-life for this reaction? So the same way we did the integrated loss, we have also gone ahead and defined the formulas for the half-life. So this will be the half-life for a first order reaction. This will be the half-life for a second order reaction, the half-life formula. And this will be the one for a zero order reaction. So given the K, do I know which one do I need? Given the K, how do I know which one I need? So I have to show you another trick. We know that the Rayleigh law for a first order reaction is is that, right? We know that rate from way at the beginning of the chapter is nothing more than the change in concentration divided by the change in time. So molarity per seconds. We know that the concentration is molarity, and in this case is to the first order. So what will be the units for decay? So if you have a first order reaction, to get molarity over seconds, when you're multiplying molarity by something, this will have to be 1 over seconds. So molarity times 1 over second gives you molarity over seconds. So for a first order reaction, the value of the K is molarity over seconds, which is the same as molarities times seconds to the minus 1. Sorry. Let me do that again. That was wrong. Let me do it again. So the value of the K is going to be 1 over second. Because when you multiply by the molarity, you get the rate, which is molarity over seconds. So the rate constant for a first order reaction is 1 over seconds, which is the same as second to the minus 1. What about second order reaction? If you have a second order reaction, you will have rate equals K times the concentration to the second, right? We know that the rate is molarity per seconds. The concentration is molarity to the square, right? So what would the K have to be that multiplied by this gives you that? And the answer would be 1 over molarity seconds. Because if you multiply n squared times 1 over molarity seconds, that gives you n over seconds, which is what you're looking for. So that will be the unit for the rate constant for a second order reaction, which is the same as m minus 1 s minus 1. The minus means the denominator. What about zero order? The rate law for zero order is R equals K concentration to the 0, which is the same as anything to the power of 0 is the same as 1, right? So R equals K. So if R equals molarity per second, then K will have to be molarity per seconds, because molarity per seconds multiplied by 1 gives you molarity per second. So which is in another way would be m s to the minus 1. So s to the minus 1, that would be for first order. m to the minus 1 s to the minus 1, that would be for second order. And n s to the minus 1, that would be zero order. So now that we know that, let's go back to this problem. And the first question is, so the first question is, what is the half-life for this reaction? It's giving us the K, so we can see that this is first order, because that's what first order looks like. So not that one, not that one. So this is the formula I used to calculate the half-life for a first order reaction. So what is the half-life? Well, T1/2, which is the half-life, is going to be 0.693 divided by 1.42 times 10 to the minus 4 S. Actually, this should be, sorry. That should be just S like that. So that should be our, sorry, go back here. So that should be our value there. That would give us our half-life once you do that operation. So what about, sorry. So what about the second question? How long will it take for the reaction of SO2 to decrease to 25% of its initial concentration? We know this is first order, right? So ln SO2Cl2 at time, that's what we're looking for. We're looking for that time equals minus KT plus ln SO2Cl2 initial concentration. It doesn't give us the initial concentration, but we know that we want to know the time that it takes for the initial concentration to make it all the way down to 25%. So we can put 100 in here and a 25 in there, since that's what we're dealing with, right? We know the K. Now we know this value. Now we know that value, so we can find the T. So you can do the math on your own. So we can find the T by solving for those equations. And that would be the time that it takes to go from the initial concentration to 25%. And then we have an easier question after that. Why do I say it's an easier question? Well, let me show you. This is the formula that we're looking for. So that's the formula for the first order reaction. So now, if the initial concentration is 1 molar, so it's giving us the initial concentration 1 molar. How long? So we're still looking for time. So that's what we're looking for, time. Will it take for the concentration to decrease to 0.78? 0.78. We know the K, right? This is the value of the K. So we know that. So that's just more math problems. Just plug everything on your calculator and solve for T. What about the last question? If the initial concentration is 0.150, so if the initial concentration is 0.150 molar, right? What is the concentration after this many seconds? So now it's asking for this, right? After 2.00 tends to the second seconds. We know the K value, that's right there. So we know this. We know that. We can calculate that. So that's going to give us this value. And then all we do is the inverse of that value. So once we get this value, all we have to do is do the E to cancel that and do the E to the number that you get over here. And you can do the same thing with that. If you can do it with 2 seconds, right? 2 10 to the second seconds, you can do it with 5. So that's how we approach that. So super important that you can recognize based on the units of the constant, based on graphing y versus x and getting a straight line and so on, recognize what order you're dealing with. Because once you know what order you're dealing with, then you have all these formulas that you can immediately begin to use. First order, second order, and zero order. And this is your daily work, 15.7. And with that, I can say that we saw how by taking measurements of concentration and time, we can find a lot of information when we start using the integrated rate law. You can also combine that with the regular rate law, right? And that will allow you to do make predictions of time or concentration remaining. And you can even do a stoichiometry to predict the amount of product you're going to be making. And we saw also that we can, in terms of time, we can specifically be talking about the half-lifetime, because that's a very important concept that we're going to see repeating in a lot of the chapters we're going to cover. And with that said, that's the end of these sections. So when we come back, we will continue talking about the kinetics of chemical reaction. I will see you later. Take care.